So we are now ready to talk about this concept of a surface integral, surface integrals. So let me remind you that we already know about doing double integrals. So double integrals, typically we would do this in XY space. And what you'd have is you're trying to do an integral of this form. So you've got some function which is on XY space, f of xy. And what you do is you integrate with respect to the area element, which is dx dy, and that's actually going to be dA, which is a tiny area element which you choose in this object, this domain over integration. And then what you're doing is that you're essentially integrating over all of these, right? You're adding together all of these quantities, and a typical application of this would be if f of xy is a density of a plate, so density in the sense of mass per unit area, then when you do this calculation, you're going to get the mass of the tiny element, and then you just add everything together, you get the mass of the entire plate. Okay, so double integrals, we can do this on flat surfaces. So what we're going to try to do in this section is to try to extend this. So this is the first of 4 lectures that we're going to do on surface integrals. So extend this to curved surfaces, right? So let's suppose you've got some curved surface which I've drawn over here, embedded in R3. Right, so think of this like a bowl or something like that, or this can be even the sphere, right? So just any old surface which is embedded in R3. So now this is a 2-dimensional surface. But it's curved. It's no longer flat, and that's going to cause us all sorts of difficulties. So what we're going to do is, once again, just like you had an area element in the previous case, we're going to think of this as what I'm going to call a surface element. So I'm not exactly going to call this an area element because it's actually a curved object, right? So you take a tiny infinitesimal sort of element which lies on this surface. Okay, so that's what I'm going to call a surface element, but it's essentially analogous to an area. But it's curved. So what we want to make sense is of integrals of this form. So you have a function which is a scalar field, but now your domain is R3. So your scalar field it takes on values in R3. So it's a function of x, y, and z. And as you go to different points on this surface, you're going to get different values of the function f. So what you're doing now is you're going to take that function, multiply it by this ds, this surface element. And once again, we can make sense of this exactly as in the previous case. We can think of this as trying to find so the mass of, say, a bowl. So this S might be some sort of bowl made out of plastic whose mass is variable at different points. And then this is going to give you the mass of this little element over here. And then you add everything together. Right, so that's what you want to do. So we can think of it like that. So mass of a curved bowl would be a typical application of an integral of this form. Well, this integral actually has some difficulties. There's 2 difficulties that I'd like to point out. So the first thing is that this depends on x, y, and z because we're in R3. So there's 3 variables which are over here. On the other hand, it's a 2-dimensional integral. Why is it 2-dimensional? Well, the surface is just 2-dimensional, right? So S is a 2-dimensional entity, and you can see that I put 2 integral signs here to indicate that it's 2-dimensional. And also another sort of indication of the 2-dimensionality is the fact that this surface element is a 2-dimensional object. So it's in 2 dimensions, and so these parts of the integral tell me that it's in 2 dimensions. So I want to try to do this as a 2-dimensional integral. However, I have 3 variables here, and the problem is that as you go to different locations on this surface, all 3 variables will typically be changing, and this is kind of now very awkward to do, right? That's not dx dy, and that doesn't make sense either because z is changing as well. So exactly how do you do this integral? So that's what we want to make sense of in this lecture. That's it. We'll just try to make sense of how you can understand this integral, and we'll talk about more different integrals and do some more examples in the other lectures as well. Okay, so the main point here is that 2-dimensional surfaces, it's 2-dimensional, right? So you can parametrize this using 2 parameters. So what do I mean by that, right? So let's suppose I got my surface like this. Well, what I can do is I can think of there's 2 parameters, u and v. Right, so given a value of u and given a value of v, that defines a unique point on this surface. That is a parametrization of this surface. So a parametrization is nothing more than just trying to find a coordinate system for the surface, right? So one way of thinking about the coordinate system is that, well, in your standard rectangular coordinate system x and y, well, you have x equals constant lines which look like that. and y equals constant are lines which look like that. So any general point is a point of intersection between x equals constant line and a y equals constant line. So x and y are coordinates, and you can think of these as parameters as well. Well, similarly, so on the surface, if you have u equals constant, well, curves in general, a whole bunch of u equals constant curves, that's u equals 1, u equals 2, and so on. And you have v equals constant curves. And as long as these intersect transversely, they're non-tangential, then every point of intersection corresponds to a coordinate uv. Yeah. So that's a very simple way of thinking about this. A simple example is the Earth. Right, let's just think of the Earth, the globe, and if you think of the globe, we are quite used to seeing coordinates of different points given as, so many, whatever, 79 degrees east and 5 degrees north. So that's giving the coordinates in terms of a longitude and in terms of a latitude. Well, so that's exactly what's going on over here as well. So if you have the Earth like this, so a constant latitude, now this might be the equator, and this might be something further up, right? A constant latitude, I don't know, that's 40 degrees latitude or something like that. This is 0 degrees latitude. So you have constant latitude curves, which are these circles which go around. You also have constant longitude curves, right? That might be the Greenwich meridian. This might be 20 degrees east. That might be 60 degrees east, and so on. You have constant longitude coordinates as well. And at a general point, as long as you exclude the north and the south pole, at any other point, you're going to get an intersection, a nice transverse intersection, and you can define the coordinates of that point. Right. So this is a parametrization. So when I'm talking about a parametrization, it's nothing more than a coordinate system. That's it. Right. So it's a two-dimensional surface. So you can give two coordinates, and I'm going to call the coordinates u and v. Right, so you can express it in two coordinates. So in general, here's a more sort of mathematical way of thinking about this. So here's a surface. We've got some sort of surface, and here's a general point r which lies on the surface. Excuse me, but these are in x, y, z coordinates. So what we're trying to do when we're doing a parametrization is that point there, you're going to represent it with a uv coordinate. So you think of a uv plane out here, let's say, and that's going to be a uv coordinate, and corresponding to that, there's exactly one point on this side. So essentially, this is a function. We can think of this as a function or a transformation or a mapping from the uv plane, which in this indication, in this, it's flat, right? So that's actually really good. It's flat out here from the uv plane into a location in xyz space. So in other words, given any point uv over here, there's an r, and what that means is that if there's an r, well, there's an x coordinate, there's a y coordinate, and there's a z coordinate. So I can write the position vector on this in this particular way, and then what I need to do in order to describe the surface is I need to know what the limits of u and v are. Right, so it's the limits which cover this object over here. So I'm going to have some limits in u and v in order to represent this surface. So the advantage now is that each point in the surface, I'm thinking of it in terms of just two quantities, u and v. Okay, now let's try to figure out this surface element, this differential surface element. That's really what I want to do. Okay, so in order to do that, I'm going to continue to think of this transformation R between the UV plane and this actual location. So here's your general point UV, and that maps to a point R, right? So that's a general point. Now let's suppose I increment one of the parameters. So I have u and v. Let's suppose I just increase. Increment means just increase slightly one of them, and I'm going to increase it by an infinitesimal amount du. Right. So when I do that, I'm going in that direction. So I get a new point over here. Now, what happens to that point if I map it according to this? Well, that's going to get mapped to some point which also lies on the surface, of course, right? It must lie on the surface because that's the way in which we use the parametrization, right? So there's an equivalence between points over here in this domain and points on the surface. So this new point, which is very close, this new u value, well, that maps to a point over there. So I have a vector over here corresponding to this little change that I made, and that's going to give me a vector on this side corresponding to the change that I made. But this is an infinitesimal change, and since both of these lie on the surface, this is essentially a tangent vector to the surface because both of them must lie on the surface. I'm going to call that dr for now, right? And one thing that I know is that dr, using your standard your chain rule, your dr, right, which is this vector over here, I can write it in this way, right? So it's d this map with respect to the derivative of the map R with respect to U times the change in U. That's your standard chain rule applied to this. Well, we can write this a little bit more. We can expand on this, because the point is that R actually has coordinates X, Y, and Z. So R is Xi plus Yj plus Zk. So when I take the derivative, it's going to be, well, the derivative of X with respect to Ui, derivative of Y with respect to Uj, and derivative of Z with respect to Uk. And then I got my du here as well, right? So my dr vector is going to be given by this. Now I'm just going to add a little subscript of 1 to this, right? Because I'm going to have a dr2 in a moment as well. So dr1, which is the vector that I get by incrementing u by a small amount in parameter space, in my uv parameter space, and I have a nice little expression for this, right? So what is the expression? Well, it's just the derivative of r, my position vector with respect to u, times du. Or I can expand it out like this. Well, let's suppose I do the same thing now with v. Yeah, so I change v to v plus dv. So here was my original location. So I change it. So I increase v by a small amount. So I go in that direction, right? That's the increase in v. And then I have a new point over here. That point is going to map to a point that I have over here. So I'm going to get a new point over there, which I get mapped to. And what I want to do is I want to make sense of this vector that I generate over here, right? I'm going to call that dr2. Well, it's exactly the same argument, right? So dr2 is going to be dr by dv times dv, because I'm only changing v, and I can write it in that way. Okay, so now what I've done is I've looked at two different things over here. So this is sort of a expanded out. I've zoomed in, if you like, to the infinitesimal elements in those two different, in this left diagram and in the right diagram. I've zoomed out. So what have I done over here? I've done two things. I had my initial location uv. I thought of incrementing u by a small amount du, and incrementing v by a small amount dv, and I generated these new points in my parameter space. Well, I can draw a little rectangle there, and this is going to be my area element in uv space, right? That's my area element, and we know that this is, I can write this as du dv. Fine, but what happens in real space? In real space, where we are is we're out here, right? We're on this two-dimensional surface, which is a curved surface, and it lives in R3. So what happened? So I had a location R, and then this is what I got. This is what I call dr1. That's what I get by mapping this line, essentially, right? That's what happens when I change u by a small amount, and if I change v by a small amount, I get that line over here. Okay, so what I can do is now it's this angle need not be 90 degrees. There's no reason for it to be 90 degrees at all, but I can draw a parallelogram here, and this parallelogram, I'm going to think of this as my surface element. Right? It's an infinitesimally small quantity. It's a differential element. I can think of this as my surface element on the surface here. Right? So it's a surface element which I get by I generate by looking at these two things, and I get this from this sort of parallelogram that I get. Well, okay, but I want to know the area of the parallelogram. So to find an area of a parallelogram, this is something which you're familiar with, I'm sure. So one thing you can do is you can drop a perpendicular down here. And if this angle happens to be theta, this distance is dr2. So this is dr2 sine theta. This length is dr2, the size of dr2 times sine theta. So what I have to do to find the area of this parallelogram is I need to multiply that distance by this distance. And that distance is just the multitude of dr1. So it's going to be the norm of this times the norm of this times sine theta. Okay, that's going to be my area of the parallelogram. But of course, if you remember, that's just exactly what you get by taking the cross product, right? So you take the cross product between these two vectors, and that gives you that sine theta, and then you take the norm of that, the size of that, and then you're done, right? But we already know what dr1 is. So dr1 is this thing over here. It's using the chain rule, it's that, and dr2 using the chain rule is this thing over here. So this is a vector, of course. That's not a vector, that's just a scalar quantity. That's a scalar quantity as well. So when I take the cross product between these two, I can just pull out the du and the dv. I can pull them out here. I can pull them out of the norm sign, and I'm thinking of these as positive quantities. So what I have is the derivative r with respect to u crossed with the derivative of r with respect to v, and then I need to take the norm of that, the magnitude of that, and multiply that by du dv. That gives me ds. That gives me my area element. Right. Okay, so here's summarizing what I just said. So what I have, here's the surface, right? Here's my true surface in R3. So I have a tiny little element over here, and that ds. So the area of this I can calculate in this particular way, right? I'm using the subscript notation now for the derivatives for convenience. So the derivative r with respect to u, derivative cross with the derivative of r with respect to v, and then I've got a du by dv, and I've got these norm symbols, right? And a reminder, so we parameterize the surface, so we think we know what r is as a function of u and v, and that corresponds to the x, y, and z coordinates. So of course we can calculate the derivatives of this, right? So in order to calculate that, we can calculate the derivatives of this. We can do that, and we can do the cross product because everything's written in terms of I, j, and k. We know how to do cross products related to that. So this is the surface element. Okay, we are making good progress here, but it turns out that you can be a little bit more clever. If you look at the surface element, it's a scalar quantity because it's just going to give me the area of that surface over there. And how did I generate that? I took this cross product. I took this cross product, and then I looked at the norms of those, right? Now, what if I'm just being a little sneaky and I just get rid of these norm symbols? Right? I just get rid of the norm symbols. What do I get then? Well, I'm going to call this the vector surface element, right? So these norm symbols were there earlier. I've got rid of this. I'm going to call this a vector surface element. Why is it a vector? Because when I take a cross product, I'm going to get a vector. So I'm going to have to put a line under the ds. Right, so here's a vector surface element. Now, what on earth does this mean? Okay, well, so let's see. So what is the size of this? Well, the size of this is going to be the size of this side, and these things are scalars, so it's just going to be the size of that. Okay, so here's a vector, which is fine. And when I'm thinking of a vector, the norm of that, the size of that, then is just the actual area. Okay, so if I define this vector surface element, its size gives me the area. But what about the direction? A vector has two things, right? So what about the direction? What does that give me? Well, that direction is kind of interesting to try to figure out, right? Because what you have here is that you have, when you're taking RU, that's a vector which points along one side of this parallelogram. RV points along the other side of the parallelogram, and both of these are tangential to the surface. It's an infinitesimal little quantity. It's tangential to the surface. When I take the cross product, a cross product is going to be perpendicular to both of these individual vectors. So it's perpendicular to this, and it's perpendicular to this, but these are two different independent vectors which are tangential to the surface. So when I take the cross product, that means I'm going to be normal to the surface, right? So that's going to be something which points in that direction. So ds is going to be pointing in the normal direction to the surface, orthogonal to the surface. It's going to be orthogonal to the surface. It's not clear to me whether it's pointing in that direction or whether it's pointing in the other direction, but no matter. It's going to be normal to the surface in that case. So this is kind of clever. If I define this vector surface element in this particular way, its size, its norm just gives me my standard scalar surface element, which is just the area of that quantity. But I'm encoding some additional information. If I think of this vector surface element, I'm encoding the direction as well. Yeah, and this is kind of important when you have two-dimensional surfaces which are embedded in R3, because the surfaces are curved. If I take a different location over here and I draw the surface element, the normal vector is going to be pointing in a different direction. So having this information turns out to be kind of useful to us as we proceed onwards. Okay, so we've defined the vector surface element. Now, okay, the whole point here, my motivation here was how to compute an integral of this form, right? So we had some given function, and we're trying to integrate this over a surface. Well, here's how we do this then, right? So the difficulties we had were we had these three variables over here, but we want to write everything in terms of two variables. So the whole idea is to parameterize the surface in terms of these two variables, so u and v. So we need to be able to figure out a parameterization for the surface. And once you've got that, the idea is that you express everything in this integral in terms of uv. That's it. Right, so it's as simple as that. So what do I mean by everything in the integral? Well, I've got this integrand first. So that integrand, I write it in terms of u and v. Well, I can do this because I presumably I know what this parameterization is. So I know what x is as a function of u and v, and so on. So I can write this completely in terms of u and v. So that part is done. What about this part? And this is the difficult part, and that's what we had to spend some time on. That's your surface element. And this is just the area, sorry, the scalar version of the surface element in this case. And that's given by, well, it's given by this thing over here. right? Because we know what r is as a function of u and v, we can do this calculation, and then we can calculate the norm and convert that to du dv. And this is great because now we are going to have du dv. So we are going to express everything in terms of u and v. The other thing we need to do is we need to write down the limits. Well, when I parameterize this surface, I know what the u and v limits are. So I can convert this whole thing into u and v. So that's the idea, right? So you convert this completely into integrals with respect to du dv. So it's essentially a double integral now. Yeah, so this two-dimensional surface, curved surface embedded in R3, we've converted it into a flat integral, a double integral in flat UV space. There is a little caveat to this, a little sort of thing to worry about. And this is the fact that the normal vector must vary continuously along the surface S for the integral to be well defined. It has to vary continuously. It cannot just suddenly flip to the other side or do something crazy like that. And this, in mathematical notation, in terminology, this is saying that the surface S must be orientable. There has to be an orientation to it. Now, here's an example of something which does not work. So you probably heard of the Mobius strip. So in the Mobius strip, you take a long strip like this of paper, and then what you do is you just sort of flip. You flip one of these sides, you move it to the other side, and you tape it together, right? So if you're an ant which is on the surface, you keep going along the surface like this. You keep going. By the time you come around, you're actually on the other side of the surface because you've done a flip when you tape the two surfaces together. So thinking about this in terms of the normal vector is that, okay, you make some choice, right? It's a two-dimensional surface. You make some choice of the normal vector. You keep following it. Yeah. So think of this, think of this as an ant with carrying an antenna on its head, right? An antenna pointing directly upwards. So it's pointing directly upwards. You go around, but by the time you come around, the ant is on the other side, so it's pointing in exactly in the opposite direction. So it doesn't vary continuously as you go all the way around. So in this case, in general, we are not able to define integrals of this form. But as long as the surface S is orientable, and of course you need other conditions on F, right? So F has to be integrable over the surface S. So of course, if you have nice properties like continuity and piecewise continuity, that's sufficient in order to do this. And that's how you make sense of an integral of this form. So the theory for this is a little bit complicated because you've got this, which is why I spent one lecture on this. So what we'll do in the next lecture is we'll do an example on this, and then as we continue on, we'll talk about different types of surface integrals as well.